You are already familiar with the composition of the atmosphere. Nitrogen and oxygen are the major atmospheric gases, and other gases such as argon and carbon dioxide are in minor amounts. Water vapor is also present in the atmosphere in wet air. Apart from the major and minor gaseous components, the atmosphere also contains some species which locally alter the chemical composition of air. In this module, we will discuss reactions of these species in detail. As we know, according to the kinetic molecular theory of gases, the molecules present in the atmosphere are moving and colliding together continuously. In the daytime, solar radiation is continuously delivered to the atmosphere. As a result, the molecules are in motion, and the molecules present in the atmosphere absorb the light energy and photochemical reactions take place, which would not occur under normal atmospheric temperatures without light. To determine the nature of chemical species, including pollutant species in the atmosphere, photochemical reactions play a crucial role. We will discuss this in further detail. After studying this module, you will know about photochemical reactions in the atmosphere, sources and effects of photochemical reactions, gases involved in photochemical reactions, smog and its formation, types of smog, that is industrial and photochemical, and the differences between them, factors affecting smog formation, and mitigation measures for photochemical reactions. So, talking about chemical and photochemical reactions in the atmosphere, we know that nitrogen dioxide, which is present in air, is photochemically active due to the presence of an unpaired electron. Nitrogen dioxide molecule reaches a higher level of energy when it absorbs a photon of light with energy h nu, which converts the ground state molecule to an electronically excited state molecule, here designated by an asterisk. So, NO2 plus H nu gives NO2 in the excited state. The excited molecule NO2 star may quickly re-emit a photon of light exhibiting luminescence. So, instant re-emission of light is called fluorescence, and if the light is emitted after a significant delay, it is called phosphorescence. Alternatively, photodissociation may also occur, that is when energy results in the breaking of an NO bond and produces a nitrogen monoxide molecule and an oxygen atom. NO2 plus H nu would then give NO plus O. Both of them are free radicals as they contain unpaired electrons. Photodissociation of molecular oxygen results in two oxygen atoms, O2 giving O plus O. Free radicals such as an oxygen atom immediately react with another atom or molecule. Most of the radicals present in the atmosphere are highly reactive and exist only for a short time, but the NO2 molecule is not so reactive and therefore it can exist in the atmosphere for a longer time. Chemical species in the atmosphere excited due to absorption of light may also undergo photoionization through a loss of an electron. So, N2 star can give N2 plus electron, and excited species may also react directly with another species. O2 star, that is O2 excited molecule, plus O3 ozone gives two oxygen molecules in the ground state and an oxygen atom. Other phenomena undergone by excited chemical species may be intermolecular energy transfer or intramolecular energy transfer. N2 excited plus O2 giving N2 plus O2 star, or XY in an excited state giving XY in another excited state, here denoted by a different symbol. Let us now talk about smog. Smog is an air pollution phenomenon. The term is derived by the combination of two words, smoke and fog. Smog basically is of two types: industrial smog, which is also called London smog, and photochemical smog, which is also called Los Angeles smog. The Industrial Revolution has been the main reason for the increase in atmospheric pollutants over the last 3 centuries. Since the late 1700s, London, the place of origin of the Industrial Revolution, experienced occurrences of smog. The incidence of smog increased in frequency throughout the 19th century and the first half of the 20th century. In the worst reported smog incident, which occurred in 1952, around 4,000 people were killed. Smog in London is also known as sulfurous smog. Smog formed by smoke from coal fires contains a high percentage of particulates. These particles bind with the fine water droplets in fog to create a dirty mist. Its main toxic chemical constituent is sulfur dioxide. Photochemical smog, on the other hand, is driven by radiant energy from the sun. The primary chemical constituent of photochemical smog is nitrogen dioxide, which is formed by the combination of nitric oxide with oxygen. The brownish tinge characteristic of Los Angeles smog is because of nitrogen dioxide present. In the atmosphere, in the presence of sunlight, ozone and peroxy compounds are formed, which are corrosive in nature. Industrial and photochemical smog can be differentiated on the basis of weather conditions, content and source, as you can see in the table. Industrial smog is in mostly cool and damp weather conditions and consists of particulates and sulfur oxides. The chief source is coal combustion because coal contains a lot of sulfur. Photochemical smog, on the other hand, takes place in sunny weather. The content is mainly nitrogen oxides, ozone and hydrocarbons. And the chief source is, in this case, gasoline combustion, that is petrol combustion in internal combustion engines, that is from vehicular exhaust. Formation of photochemical smog. Formation of photochemical smog is due to a sequence of reactions. Nitrogen oxides, the mixture of NO and NO2 together referred to as NOx, and volatile organic compounds, VOCs as they are sometimes called, are primary air pollutants released in the atmosphere by automobiles and industrial processes. Nitrogen dioxide absorbs ultraviolet light and formation of nitric oxide and atomic oxygen takes place. Ozone is generated by the reaction of oxygen gas with this atomic oxygen created. Aldehydes and peroxyacetyl nitrate so formed are thus secondary air pollutants. Photochemical smog therefore can be called a mixture of primary and secondary air pollutants. Motor vehicles are responsible for production of exhaust gases rich in oxides of nitrogen, which include nitrogen dioxide and nitric oxide. At the high temperatures in a car's combustion chamber, nitrogen and oxygen from the air react to give nitric oxide, and the nitric oxide so formed then reacts with oxygen and nitrogen dioxide is formed. In the presence of sunlight, nitrogen dioxide molecule present in high concentration breaks up and gives oxygen atom. NO2 plus a photon of light H nu gives NO and O. This atomic oxygen reacts with oxygen molecule present in the atmosphere and ozone is formed, O plus O2 giving ozone. Ozone so formed then reacts with NO to form NO2 and O2. The reaction in which ozone is formed is dominant when the ratio of NO2 to NO is more than 3. If the ratio is less than 0.3, however, the nitric oxide so formed results in destruction of ozone at the same rate as that of its formation and results in lowering the concentration of ozone to less harmful levels. The reactions of hydrocarbons from unburned petrol with nitric oxide and oxygen in the presence of sunlight generate aldehydes, ketones and peroxy compounds. A part of the ozone formed above reacts with volatile organic compounds such as hydrocarbons, especially olefins, also released from auto exhaust, giving carboxyl free radical, RCO2 free radical. So ozone plus hydrocarbon RH giving RCO2 radical plus RCHO and R2CO, that is aldehydes and ketones. The free oxygen atoms formed then react with hydrocarbons to produce alkyl or aryl free radicals as well as acyl free radical RCO. So O plus RH gives R radical and RCO radical. Similarly, RCO radical plus oxygen giving RCO3 radical. Acyl peroxy radicals may also be formed by the reaction of carboxyl radicals and oxygen atoms. RCO2 radical plus oxygen atom giving RCO3 radical. Any acetyl peroxy radicals formed during this process further react with nitrogen dioxide giving peroxyacetyl nitrate, also known as PAN or PAN. CH3CO3 radical plus NO2 giving CH3CO3NO2. If the peroxy radical reacting with nitrogen dioxide has an aromatic ring as substituent, then you can get peroxybenzoyl nitrate PBZN. C6H5CO3 radical plus NO2 giving C6H5CO3NO2 or peroxybenzoyl nitrate. Now let's have a look at effects of photochemical smog. So all the major constituents of photochemical smog are detrimental to human health and the environment. Being a cocktail of chemical oxidants such as ozone, nitrogen dioxide and peroxy compounds, it is often termed as oxidizing smog. The brown nitrogen dioxide in smog affects visibility. Nitrogen dioxide, ozone, VOCs and peroxynitrates all result in eye irritation and respiratory problems. Prolonged exposure to NO2 lowers resistance towards respiratory infections. Apart from being irritants to the eyes and the respiratory tract, some VOCs are also believed to be carcinogenic. Ozone has a harsh odor and causes coughing, wheezing and eye irritation. Ozone also causes oxidative damage to plant and animal tissue. PAN causes irritation in eye and respiratory problems. It is considered to be more toxic than ozone for plants. Let's have a brief look at the sources and environmental effects of the various constituents of photochemical smog. Nitrogen oxides, that is NO and NO2 together. The anthropogenic sources are combustion of gasoline in automobiles and gasoline, coal gas in industry. Environmental and health effects are, it would decrease visibility due to the yellowish brownish color of NO2. High levels of NO2 exposure gives rise to cough and shortness of breath. There will be irritation in the eye. It may increase cases of cancer. NO2 is also responsible for suppressing growth of plants. Nitrogen dioxide, when exposed to in high concentration, increases respiratory infections. Nitrogen dioxide also reacts in the atmosphere to form acid rain, which can harm plants and animals. So further comments about this is that only 5% of the total concentration of nitrogen dioxide results from combustion, and most of it is formed from reactions involving NO from lightning, bacterial action in soil and volcanic activity. But though only 5% is anthropogenic, it is enough to upset the balance of nature. Now the volatile organic compounds, they are caused due to evaporation of solvents, evaporation of fuels and incomplete combustion of fossil fuels. They cause eye irritation, respiratory irritation. Some are known to be carcinogenic. They also cause decreased visibility due to blue-brown haze. VOCs in the atmosphere include naturally occurring compounds such as terpenes which are released by vegetation. Ozone is formed because of the photolysis of NO2, as we have seen above. It has a harsh odor. It causes bronchial constriction, coughing and wheezing, respiratory irritation. It breaks down rubber and damages plastics, retards plant growth, decreases yields of crops, and also causes major eye irritation. So the additional comment is that people with asthma and respiratory problems are mostly affected by it. 0.1 ppm concentration of ozone can reduce half of the total photosynthesis that occurs. Peroxyacetyl nitrate, PAN, and related compounds. These are formed by the reaction of NO2 with VOCs, as we have seen earlier. They cause eye and respiratory irritation, affect plants, and cause damage to proteins. PAN had not been detected until it was recognized in smog. It has higher toxicity to plants than ozone. There are certain factors affecting the formation of photochemical smog. High concentration of nitrogen oxides and VOCs are associated with automobile exhausts and emissions from industry, where this combination of substances arises due to fossil fuel combustion. The concentration of photochemical smog present in the atmosphere varies with the time of the day. You can see in the graph shown here the daily variation in the composition of photochemical smog. The graph suggests that as the traffic in the early morning increases, the concentration of nitrogen oxides and VOCs also increase. This is the legendary rush hour when everybody is going to work. But as the traffic decreases later in the morning, the reaction between nitrogen oxides and volatile organic compounds takes place and nitrogen dioxide is formed, which results in increase in the concentration of nitrogen dioxide. Around noon, the intensity of sunlight is high and it results in the breakdown of nitrogen dioxide and formation of ozone. At the same time, some of the nitrogen dioxide can react with the VOCs to form PAN and other toxic chemicals. Ozone and the peroxy compounds are together depicted here as oxidants. As the sun goes down, the production of ozone and PAN ceases. There are several reactions which result in the consumption of the ozone and other oxidants present in the atmosphere. There are also meteorological factors affecting the formation of photochemical smog. Rain can dissipate photochemical smog as the pollutants are washed out of the atmosphere with rainfall. Photochemical smog can also be blown away by wind and result in replacement by fresh air. However, temperature inversion is a factor which can cause increase in the impact of photochemical smog. Normally during the day, air which is near the Earth's surface is warmed and rises up, carrying pollutants with it. However, a temperature inversion traps pollutants near the surface of the Earth. A temperature inversion is a phenomenon in which the normal tropospheric decrease in temperature with height changes to increase in temperature with increasing height. A temperature inversion thus traps a layer of cold air beneath warm air, reducing mixing of the atmosphere due to convection. Dispersion of pollutants therefore decreases. Inversions can remain in place for some days, which may stretch to several weeks. Topography is another factor which also affects the smog event. Towns located in valleys are more affected by photochemical smog because the surrounding hills and mountains reduce airflow, allowing the amounts of pollutants to rise. Valleys are also sensitive to photochemical smog because there is a stronger tendency for temperature inversion to take place in valleys. We must now look at mitigation measures for photochemical smog. The Great Smog of 1952 in London led to the Clean Air Acts of 1956 and 1968 in Great Britain, which resulted in banning of black smoke emitted by industries and conversion to smokeless fuels. Since then, things have started improving and the extreme smog formation episodes have not been repeated in London. Control regulations for automobile emissions and stress on clean energy in California have resulted in improved quality of air in Los Angeles, according to a 2013 study sponsored by the National Oceanic and Atmospheric Administration. According to this study, levels of chemicals initiate smog formation have decreased along with levels of ozone and peroxyacetyl nitrate. Many other cities in the world have the problem of photochemical smog. These include New York, Chicago, Vancouver and Delhi. There are some general mitigation measures which could be applied globally, the foremost being catalytic converters for automobile engines. Let us discuss this in detail. Catalytic converters. Smog formation could be reduced if the amounts of oxides of nitrogen and hydrocarbons released in the atmosphere decrease. This is done by installing efficient catalytic converters in automobiles. A two-way catalytic converter consisting of a mixture of platinum and palladium supported on a ceramic or metal honeycomb bed removes hydrocarbons and carbon monoxide from the exhaust. It is an oxidation catalyst which converts CO to CO2 and hydrocarbons to CO2 and water when the exhaust gases are forced through it. So 2CO plus a molecule of oxygen would give 2 molecules of carbon dioxide. And similarly, RH, hydrocarbons plus oxygen would give CO2 and H2O. A three-way catalytic converter consists of a mixture of platinum, palladium and rhodium deposited on a high surface area ceramic and metal honeycomb or alumina pellets, and it removes hydrocarbons, carbon monoxide and nitrogen oxides from the exhaust. The converter contains an oxidation reduction catalyst mixture. Hydrocarbons and carbon monoxide are oxidized while nitrogen oxides are reduced. In the exhaust system, the nitric oxide reacts with carbon monoxide to give nitrogen and carbon dioxide. So 2NO plus 2CO over the catalyst gives N2 and 2CO2. If NO is only partially reduced to N2O, the converter would still work because N2O is easily decomposed. 2N2O passed over the catalyst gives 2N2 and O2. NOx and hydrocarbons interact amongst themselves to give nitrogen, carbon dioxide and water. NOx plus RH mixture passed over the catalyst gives N2 plus CO2 plus H2O. A three-way converter operating under stoichiometric conditions of air-fuel ratio 14.6:1 and at temperatures of 400 to 600 degrees Celsius can achieve almost 90% efficiency in removing all three offending emissions from automobile exhaust. Free radical traps. This is another mitigation measure. Certain compounds can act as free radical traps when sprayed in the atmosphere. They result in the production of free radicals themselves when sprayed, which readily combine with the free radical initiators of photochemical smog, such as O, R, ROH, etc. The introduction of such compounds will slow down the conversion of NO to NO2 from the usual 2 to 6 hours to 6 to 12 hours. Thus, the conversion will take place around the time of sunset, and photochemical decomposition of nitrogen dioxide, which is the smog initiation step, would be inhibited. The compound diethyl hydroxylamine has been found to be effective in inhibiting smog in lab tests. Though it is cheaper than catalytic converters, it has an unpleasant odor at greater than 0.5 ppm concentration, and that is certainly a disadvantage. Petrol reformulation is also something which has been tried out in many countries. In some European countries, for example, they have something called summer petrol, which is a reformulated gasoline in which 1/10 of the aromatic hydrocarbons have been replaced by oxygenated fuel such as methyl tertiary butyl ether. These additives allow more complete and efficient combustion, thus suppressing the emission of volatile organic compounds. The emission of nitrogen oxides is reduced since petrol containing oxygenates burns at a lower temperature. Decreased emissions of VOCs and nitrogen oxides also suppresses smog formation. And of course, we could come to alternative energy sources. In case we are not using anything in the automobile which can give out these offending emissions, that is, we'll have to stop using fossil fuels. So hybrid cars, hydrogen fuel cars, and cars run on different types of biodiesel may be viable methods of cutting down on vehicular exhaust emissions in the near future. To summarize what we have learnt in this chapter, we learned about photochemical reactions occurring in the atmosphere in the presence of sunlight. This type of reaction proceeds by excitement of molecules and emission of energy by the excited species in accordance with different mechanisms. Under normal conditions, the atmosphere is affected by many photochemical reactions, and simultaneously these are reactions taking place, and these, if occurring in a polluted environment, there could be many more types of reactions because a polluted environment will contain many more chemical species. We have discussed about nature and effects of photochemical reactions. We have also talked about harmful effects of some photochemical reactions and mitigation measures for such reactions. We have also discussed the phenomenon of smog and types of smog, that is industrial and photochemical, and the differences between them. Photochemical smog is driven by the radiant energy from the sun. The chemicals comprising photochemical smog are nitrogen dioxide, which is obtained by combining nitric oxide with oxygen, as well as ozone, aldehydes, ketones and peroxy compounds. We have also discussed the factors affecting formation of photochemical smog, the effects of such smog and its mitigation measures. Control regulations for automobile emissions and stress on clean energy in California have resulted in improved quality of air in Los Angeles, according to a 2013 study sponsored by the National Oceanic and Atmospheric Administration. According to this study, levels of chemicals initiate smog formation have decreased along with levels of ozone and peroxyacetyl nitrate. So now you are familiar with the photochemical reactions occurring in the atmosphere and know how these reactions alter the chemical composition of the atmosphere.